Welcome to the master course on the OWASP Top 10 Web Application Security Risks. This is a comprehensive guide designed to take you from a foundational understanding of web security to a mastery of the most critical threats facing modern applications. We will move through 4 phases: forging the foundation, dissecting the threats, architecture and maintenance, and finally, unyielding mastery. Let us begin with Phase 1. Forging the Foundation. Module 1, Foundations of Web Application Security. This module is about building the security mindset. We need to distinguish web security from general cybersecurity and define the landscape of the modern web.
Lesson 1.1, Web Application Architecture and Attack Surfaces. Imagine a bank vault. Physical security protects the heavy door. That is general cybersecurity. But web security is different. Web security is checking to see if the bank teller is secretly handing out cash to the wrong people. Your objective here is to visualize the flow of data to pinpoint exactly where attackers strike. The modern web stack consists of the client, such as a browser using React or Vue, talking to an API, which talks to a server running Node or Python, which finally talks to a database. The attack surfaces are found in 3 places. First, the inputs. These are forms, URL parameters, headers, and cookies. Second, the outputs, HTML responses, JSON data, and error messages. And third, the logic. This includes authentication flows, password resets, and payment gateways. Let's look at a practical example called the hidden input. Scenario: you are testing an e-commerce site. You see a URL in your browser that ends with product equals watch and price equals 100. The vulnerability here is that the price parameter is visible in the URL and potentially editable by the user. An attacker's action would be simple. They change the URL so that price equals 1. The solution, or the fix, is to never trust the client. The price should be looked up on the server using the product ID, completely ignoring the price sent by the browser. Here is your assessment question for this lesson. You are reviewing an architecture diagram. The client sends a user ID cookie to the server to request account details. Why is this a potential attack surface? Here is the ideal answer. Cookies are stored on the client side and can be manipulated by the user. If the server trusts the cookie without validating it or ensuring it hasn't been tampered with via signing, an attacker could change the user ID to access someone else's account.
Lesson 1.2, the OWASP Top 10 Motivation. If you know the enemy's playbook, you can predict their moves. The OWASP Top 10 is that playbook. It lists the 10 most critical security risks found in web applications globally. OWASP stands for the Open Web Application Security Project. It is a nonprofit community. The list is updated periodically based on data from thousands of companies. It matters because it is the industry standard for compliance and secure development. Here is a quick interactive engagement. If you were to look at the changes in the list over the years, you would see that the threat landscape evolves. As frameworks fix old issues, like cross-site scripting getting harder in React, attackers shift focus to new weaknesses. In 2021, broken access control moved up to become the #1 risk. Here is your assessment question. Why does the OWASP Top 10 change over time? The ideal answer is that the threat landscape evolves. As technology changes, attackers shift their focus to new weaknesses, such as access control or insecure design. Now we move to Phase 2, dissecting the threats. Module 2, broken access control. This is the #1 vulnerability. It occurs when users can act outside of their intended permissions. Lesson 2.1, Insecure Direct Object References, or IDOR. Imagine changing a number on a library card to check out someone else's books. The objective is to identify how manipulating identifiers, or IDs, grants unauthorized access. The mechanism works like this. The server receives an ID, such as user ID 123, and retrieves the record without checking if the currently logged in user actually owns that record. These IDs are often found in URL parameters, hidden form fields, or API calls. Let's look at a practical example called the invoice leak. Imagine a piece of Python code. It defines a route for getting an invoice. It takes an ID from the request and immediately asks the database for that invoice. The flaw is that there is no check to see if the current user owns that invoice. An attacker, let's call him user A with ID 50, logs in. He sees his ID in the URL. He simply changes the ID to 51. Because the code lacks a check, he can now view user B's invoice. The solution is to add a check. After retrieving the invoice, the code must verify if the invoice's owner ID matches the current user's ID. If not, it should abort with a 403 forbidden error. Here is your assessment question. You find an API endpoint for messages ending in 999. You change 999 to 998 and see another user's message. What specific vulnerability is this? The ideal answer is Insecure Direct Object Reference, or IDOR, which is a specific type of broken access control. Lesson 2.2: Forced Browsing and Missing Function-Level Access Control. Security through obscurity is not security. Hiding the admin button doesn't stop an attacker from guessing the URL. The flaw occurs when the application hides the link in the user interface, but does not protect the code on the server. Attackers use directory busting tools to find hidden paths, like /admin or /backup. Here is a practical example called the Hidden Admin Panel. A developer hides the admin panel link for standard users. However, the attacker guesses the URL site.com/admin. The server renders the page because there is no middleware checking for the admin role permission. The solution is to implement role-based access control middleware on every privileged route. In code, this looks like an authorize tag requiring the admin role. Here is your assessment question. A standard user navigates to a delete user page. The server executes the deletion. The developer argues, "But I never gave them the link." Why is the developer wrong? The ideal answer is that the developer relied on presentation layer access control, which is just hiding the button. Security must be enforced at the server layer. If the request reaches the server must verify permissions before executing. Module 3: Cryptographic Failures. This module covers protecting data in transit and at rest, and the failure to encrypt sensitive data properly.
Lesson 3.1: Password Storage and Hashing. A database breach is bad. A database breach where passwords are readable is catastrophic. You must understand why we never store passwords, only their mathematical fingerprints known as hashes. Storing a password in plain text is a fatal error. Encryption is two-way and can be decrypted. This is bad for passwords because if the key is stolen, all passwords are lost. Hashing is one way and cannot be reversed. This is good for passwords. We also use salting, which is adding random data to the password before hashing it to prevent rainbow table attacks. Here is a practical example called the rainbow table attack. Two users have the same password, 123456. If you use MD5 hashing with no salt, both passwords look identical in the database. An attacker sees the duplicate and instantly cracks both using a lookup table. The solution is to use algorithms like bcrypt or argon2. These add a unique salt to every user. Even if two users have the same password, the resulting hashes will be completely different, causing rainbow tables to fail. Here is your assessment question. You are auditing a database and see a column for user passwords. You also find a config file with an AES secret key. Is this secure password storage? The ideal answer is no. This indicates encryption, which is reversible. If the attacker steals the secret key, they can decrypt all user passwords. Passwords must be hashed.
Lesson 3.2: Sensitive Data Exposure. Sending a postcard versus sending a sealed letter. HTTP is a postcard. Everyone in the middle can read it. You must enforce encryption everywhere. Data in transit must use TLS or HTTPS. This prevents man-in-the-middle attacks. Data at rest involves encrypting the database files. And critically, regarding key management, never store encryption keys in the code repository. Here is a practical example called the HTTP login. A user logs in at a coffee shop using a site over HTTP. An attacker runs network software on the coffee shop network. They see the login request in clear text, capturing the username and password. The solution is to force HTTPS and use strict transport security headers to tell browsers never to talk to the site over HTTP again. Here is your assessment question. A developer argues, I don't need HTTPS on the About Us page, only on the login page. Why is this dangerous? The ideal answer is that if the user loads the About Us page over HTTP, an attacker can inject a malicious script into that page. When the user eventually navigates to the login page, the script is already running. The entire session must be HTTPS. Module 4: Injection. This occurs when untrusted data is sent to an interpreter as part of a command or query.
Lesson 4.1: SQL Injection. This is the classic hack, tricking the database into revealing secrets by confusing data with code. The mechanism is simple. The application takes user input and glues it directly into a database query string. The impact is data theft, deletion, or authentication bypass. Here is a practical example called the login bypass. Imagine code that says, select star from users, where user equals the username input and pass equals the password input. The attacker enters the username admin single quote dash dash. The resulting query becomes select star from users, where user equals admin, and then the dash dash comments out the rest of the query, including the password check. The database returns the admin user without a password. The solution is parameterized queries, also known as prepared statements. This ensures the database treats the input strictly as data, never as executable code. Here is your assessment question. You try to fix SQL injection by writing a function that deletes single quotes from the input. Is this a complete fix? The ideal answer is no. This is called sanitization, which is often bypassable. The only complete fix is parameterized queries, which separate code from data at the engine level.
Lesson 4.2: Cross-Site Scripting, or XSS. This is injection targeting the browser, not the server. The objective is to prevent attackers from running JavaScript in other users' browsers. Reflected XSS comes from the current HTTP request, like a malicious search link. Stored XSS is saved in the database, like a comment, and served to every visitor. Here is a practical example called the poisoned comment. A blog comment section displays comments exactly as typed. An attacker submits a comment containing a script tag that fetches the user's cookies and sends them to a hacker site. When a victim views the blog post, their browser executes the script and their session is stolen. The solution is context-aware encoding. This converts special characters, like brackets, into safe HTML entities before rendering. Here is your assessment question. Why is stored XSS generally considered more dangerous than reflected XSS?
The ideal answer is that stored XSS attacks everyone who views the page naturally, making them passive victims. Reflected XSS requires the attacker to actively trick a specific victim into clicking a malicious link. We now enter Phase 3, Architecture and Maintenance. Module 5, Insecure Design. This focuses on risks related to design flaws rather than implementation bugs. You cannot fix a bad design with good code. Lesson 5.1, Business Logic Flaws. Context: building a fortress with impenetrable walls but leaving the back gate unlocked because it is convenient for the gardener. We need to identify flaws in the workflow that allow users to bypass rules. Common flaws include skipping payment steps or manipulating quantities. Here is a practical example called the free gift card. An e-commerce site workflow allows users to select a card value, sends a request to add it to the cart, and then goes to checkout. An attacker intercepts the request to add the item and changes the price parameter from $100 to 1 cent. The solution is a server-side source of truth. Never accept prices from the client. When the client says, "Add item 55, the server looks up the price of item 55 in the database. Here's your assessment question. A password recovery system asks, "What is your pet's name?" to reset a password. Why is this an example of insecure design? The ideal answer is that the code works perfectly, but the design is insecure because the answers to security questions are often public information on social media. The architecture relies on weak secrets.
Module 6, Security Misconfiguration. This happens when security settings are not defined or default settings are kept. Lesson 6.1, Verbose Error Messages and Debug Mode. Context: a burglar knocks on the door and the house screams, "I am unlocked and the safe is in the basement." The risk is that detailed error messages reveal database types and file paths. Here's a practical example called the stack trace leak. A user enters a single quote into a login field. The application crashes and displays a 500 internal server error with a full stack trace. The attacker reads the trace and learns the server runs Python and sees the directory structure. The solution is to disable debug mode in production and configure the web server to show a generic "something went wrong" page. Here is your assessment question. You find a PHP info page accessible on a live site. Why is this a security misconfiguration? The ideal answer is that it exposes distinct details about the server environment that help attackers choose specific exploits tailored to that version.
Lesson 6.2, Cloud and Storage Misconfiguration. Leaving your file cabinet on the sidewalk. The issue is publicly accessible cloud storage buckets, like AWS S3. Here is a practical example called the Open S3 bucket. A startup uses an S3 bucket to store user photos. The bucket policy allows everyone to read data. An attacker scans for bucket names, finds it, and downloads all customer IDs. The solution is to block public access at the bucket level and use signed URLs for temporary access. Here is your assessment question. A developer leaves the .git folder accessible on the web server. What is the risk? The ideal answer is that an attacker can download the entire source code history, including potentially hard-coded API keys and database passwords. Module 7, Vulnerable and Outdated Components. This refers to using libraries or frameworks with known vulnerabilities. Lesson 7.1, Supply Chain Security. Context: you baked a fresh cake, but you used expired, poisonous milk. The cake is now poisonous. Modern apps are 80 to 90% third-party code. We must manage dependencies carefully. Here is a practical example called the Log4j nightmare. A Java application uses the Log4j library. A known vulnerability allows remote code execution if the logger processes a specific string. An attacker changes their user agent header to a malicious string, and the server executes the code. The solution is to patch immediately and use software composition analysis tools in your pipeline to block builds containing known vulnerabilities. Here is your assessment question. You run an audit and it finds a high-severity vulnerability in a library you don't recognize. Why is it there? The ideal answer is that it is likely a transitive dependency, meaning it is a dependency of one of your dependencies. Module 8. Identification and Authentication Failures. This covers failures in confirming identity or session integrity.
Lesson 8.1. Brute Force and Credential Stuffing. An attacker trying every key on the keychain until one works. Brute force is guessing passwords. Credential stuffing is using username and password pairs stolen from other breaches to try and log into your site. Here is a practical example, called the unlimited retry. A login page returns invalid password instantly, but allows the user to try again immediately. An attacker uses a script to send 10,000 requests per minute. The solution is rate limiting. Allow only 5 failed attempts per IP per minute, and use exponential backoff to lock the account for increasing durations. Here is your assessment question. Why is user enumeration dangerous on a login form? The ideal answer is that it allows an attacker to build a list of valid usernames, allowing them to focus their attacks specifically on valid accounts. The error message should always be generic, such as invalid username or password.
Lesson 8.2. Session Management Failures. Buying a movie ticket, dropping it, and someone else picks it up and walks into the theater. We must secure the session ID. Common failures include session fixation, lack of timeout, or exposing IDs in the URL. Here is a practical example called the URL token. A banking app puts the session ID in the URL. An attacker looks at the user's browser history, sees the URL with the token, and uses it to log in. The solution is to use cookies only. Store session IDs in HTTP only, secure, and same-site cookies, never in the URL. Here is your assessment question. What should happen to the session ID when a user changes their password? The ideal answer is that the current session ID and all active sessions for that user must be immediately invalidated. The user must be forced to re-authenticate. Finally, Phase 4, Unyielding Mastery. Module 9, Software and Data Integrity Failures. This focuses on making assumptions about software updates and data integrity.
Lesson 9.1. Insecure Deserialization. Serialization is freezing an object into a stream of bytes. Deserialization is thawing it back out. If you thaw a poisoned object, the application consumes the poison. The flaw is that if the application blindly deserializes data without verifying it, an attacker can modify the object to execute malicious commands. Here is a practical example called the poisoned cookie. A site stores user preferences in a serialized cookie. An attacker replaces the cookie with a malicious string containing a gadget chain. When the server deserializes it, it triggers a command that deletes files. The solution is to avoid native serialization. Use simple formats like JSON. If you must serialize, sign the data with a digital signature. Here is your assessment question. A developer says deserialization is safe because they catch all exceptions. Is it safe? The ideal answer is no. Attacks often trigger during the process of deserializing, before the application logic even takes control.
Lesson 9.2. Integrity of Updates. The SolarWinds attack. Attackers didn't hack the customers, they hacked the software update mechanism. We must verify that the code we run is the code we wrote. Here is a practical example called the man-in-the-middle update.
A router downloads firmware updates over HTTP without a signature. An attacker intercepts the request and serves a malicious file. The solution is code signing. The vendor must cryptographically sign the update, and the device must verify it. Here is your assessment question. Why is reviewing source code not enough if your build pipeline is compromised? The ideal answer is that if the pipeline is compromised, the compiler could be modified to inject a virus into the final binary, meaning clean source code produces dirty software. Module 10. Security Logging and Monitoring Failures. The blindfold vulnerability. Breaches often take over 200 days to detect because nobody is looking at the logs.
Lesson 10.1. What to log. If a tree falls in the forest and no one logs it, did the hacker get root access? You must log failed logins and access control failures. You must not log passwords or credit card numbers. Here is a practical example called the silent brute force. An attacker tries 5,000 passwords. The server rejects them, but the logs capture nothing. The admin has no idea an attack is happening. The solution is centralized logging and alerting. Send logs to a separate server and set a trigger to alert the security team if failed logins spike. Here is your assessment question. Why is it dangerous to log the HTTP request body in full? The ideal answer is that the body might contain sensitive info like passwords. If these are written to a log file, the log file becomes a goldmine for attackers. Module 11. Server-Side Request Forgery, or SSRF. This involves forcing the server to make requests on behalf of the attacker, often to attack internal networks.
Lesson 11.1. Attacking the internal network. The call is coming from inside the house. Firewalls block external attackers, but they usually trust traffic coming from the web server itself. The risk is when an attacker provides a URL pointing to an internal IP address, like localhost. Here is a practical example called the cloud metadata theft. An application has a feature that fetches an image from a URL. An attacker provides a URL pointing to the AWS metadata service. The server fetches it and displays the AWS secret keys. The solution is allow listing. Only allow URLs that match specific trusted domains. Also, disable HTTP requests to private IP ranges. Here is your assessment question. Why can't we just block the string 127.0.0.1? The ideal answer is that attackers can bypass string matching using DNS redirection or alternative IP formats. You must resolve the DNS first, check the IP, and then fetch. Module 12. Conclusion and the path forward.
Lesson 12.1. The Shift Left Philosophy. Fixing a bug in production costs $10,000. Fixing it in design costs $100. We must integrate security early. This is called shift left. It moves security from the end of the process to the design and coding phases. Here is the final assessment, your capstone challenge. You are the lead architect. A developer proposes a new feature where users can upload a zip file containing XML data, which will be parsed to update their profile. Identify 3 potential OWASP top 10 risks. Here is the ideal answer. First, injection, specifically XML external entity attacks if the parser isn't configured correctly. Second, integrity failures. Is the zip file verified against malware? And third, vulnerable components. Is the library parsing the XML updated? Course conclusion. Congratulations, you have traversed the landscape of the OWASP Top 10. You have moved from the foundation of web architecture to the mastery of structural integrity. Your final call to action is this: security is not a product, it is a mindset. Never trust input, deny by default, and practice defense in depth. You are now equipped not just to write code, but to defend it.
This concludes the Master Course.